Let us look at a very important concept in group theory, that is homomorphism. Let there be two groups with different group operations. P with the group operation star and Q with group operation as a composition. It could be any operations. Now, importantly here, these two group operations could be same. They could both be addition, they could both be composition, they both could be addition modulo of 3 or whatever, or they could be different. Similarly, the groups themselves, the sets on which these groups are built, they could also be same. So here, point is, we start off by thinking of them as two different groups, and then later on, we realize that one could be inside the other as far as the set of elements is concerned. Now, these operations star and composition what we have here, they are applicable in their individual groups. Now, the operation star takes care of the binary operations between the elements of P. Similarly, composition takes care of the binary operations of elements of Q. But what happens if we want to set up a relationship between P and Q, between two groups? Then we still have a function, but we call it as a homomorphism. So here F is the homomorphism, and there is a condition attached to it. So F is called a homomorphism. It's not a simple function. Function becomes a homomorphism if and only if F of A times B is equal to F of A times F of B, where A and B are in P. So, do you notice on the left-hand side, we have the group operation of P. And here we have the group operation of Q. If this condition is satisfied, then only we can call a function F as a homomorphism. As I mentioned, there need not be two separate groups. The mapping may exist from elements of the group to other elements of the same group. In which case, of course, we say F colon P maps to P. Let's look at some properties of homomorphism. The homomorphism preserves the operation of the respective groups. So F of A times B is equal to F of A times F of B for all A comma B in P. So be very clear. On the left hand side, you have the group operation of the first group, and here you have the operation of the second group. Identities are preserved in the sense the homomorphism will take you from the identity of P to the identity of Q. Or in other words, F maps the identity of the first group to the identity of the second group. Similarly, inverses are preserved. So F of A inverse maps to F of A inverse for all A in P. Now, there are different types of homomorphisms. So let's look at them. Let's say we have a group P, which is a group formed by the set of integers under addition modulo 4. And Q is the group generated by I under multiplication. So we have already seen this. So P is equal to 0, 1, 2, and 3 under addition modulo 4. And Q is 1, I, minus 1, minus I under multiplication. So we have a homomorphism which maps P to Q by the function f of k is equal to I to the power of k. So here, remember this condition? this condition has to be satisfied for us to call this F as a homomorphism. So for any A comma B in P, F of A addition modulo 4B is equal to I to the power of A plus B, which can be written as I to the power of A times I to the power of B. Now, I to the power of A can be written as F of A, and I to the power of B can be written as F of B. And here the Q's group operation comes. So we have a homomorphism. So the homomorphism F is 1-to-1, that is injective, and onto, that is surjective. If both are applicable, then we call it as bijective. What does this mean, 1-to-1 and onto? If you notice, if I take an element of P, it goes as an input to the homomorphism. So F of 0 is equal to I to the power of 0, which is nothing but 1. F of 1 is equal to I to the power of 1, which is I. F of 2 is equal to I square, which is minus 1. And F of 3 is equal to I to the power of 3, which is equal to minus I. So here, each element of P maps to a single element of Q. So 1-to-1. And onto is what? In Q, there is no element left out. Every element maps to or is mapped by an element of P. If there are some elements left out, then we won't call it as surjective. So when a homomorphism is 1-to-1 and onto, it is called a isomorphism. And we call it as P is congruent to Q. Naturally, if it is 1-to-1 and onto, that means the order of P is equal to order of Q. Number of elements in P will be equal to the number of elements in Q. Now let's take another example. Now remember I mentioned that we don't necessarily have to take two separate groups. Here, for clarity's sake, I have put it as two separate groups. We could have treated as a single group itself, because here also it is set of integers, here also it is set of integers. Here also it is under addition, here also it is under addition. Now, we have a homomorphism which maps P to Q by this function. F of n is equal to 3n. So here what's happening? For any A comma B in P, F of A plus B is equal to 3 times A plus B. Now that we can distribute now. So that becomes equal to 3A plus 3B. And 3A is what? 3A is nothing but F of A. 3B is F of B. So F of A plus F of B. Now, even though it is all addition, in your mind you should be clear that this is the group operation of P and this is the group operation of Q. Okay. So which means again that F is a homomorphism. Now the thing is here, domain of P, that is the set of integers, is the same as the codomain Q. If the domain is equal to the codomain, it is called endomorphism. Let's look at another example. Again, P is equal to the set of integers under addition. Q is set of integers under addition. Now, F of n is equal to minus n. So, F of A plus B is equal to minus A plus B, which can be written as minus A plus minus B. Yes, minus A is going to be what? F of A. And minus B will be what? f of b. So we have f of a plus b is equal to f of a plus f of b. So here f is 1 to 1, on to, and domain is equal to codomain. So this homomorphism is called automorphism. Okay, now let's look at other types of homomorphisms. Let's take P is equal to Z comma plus and Q is equal to Z comma plus. I'm taking simple examples just to make sure that we understand the concepts clear. And we have a homomorphism P to Q where F is equal to 2N. So F of A is equal to F of P implies 2A is equal to 2B, which implies A equal to B. So which means P gets mapped by the homomorphism to 2Z, which is a subset of Q. So Q has all the odd numbers left out of the mappings and hence not onto. So here it is 2Z, which means it is covering only the even numbers. All the odd numbers are getting left out. None of the odd numbers are being mapped from an element of P. So it is not onto. So if F is 1 to 1, domain equal to codomain, the homomorphism is called monomorphism. Of course, domain is equal to codomain is not necessary. What is important is that the homomorphism is 1 to 1 and it is not onto. Okay. Another example, or rather, another type of homomorphism. Let's say P is equal to the set of integers under addition and Q is equal to the set of integers under addition modulo 3. So F maps P to Q using this function, that is f of n is equal to n mod 3. So here f of a plus b is equal to a plus b mod 3, which can be written as a mod 3 addition modulo 3 b mod 3, which is equal to f of a addition modulo 3 f of b. So again, f is a homomorphism, but in this case, it is not 1 to 1. Remember, in Q, how many elements will be there? There will be 0, 1, and 2. Whereas Z is infinite. All those integers will map to one of these three, 0, 1, or 2. So it is not 1 to 1, it is 1 to many. Since more than one A in P maps to one element of Q. It is onto since there are no leftovers in the codomain. All the three elements in Q, that is 0, 1, and 2, are being mapped from the element of P, some element of P. It is onto since there are no leftovers in the codomain. Here, very clearly, domain is not equal to codomain. This homomorphism is called epimorphism. So let's look at a table. We have morphism type, whether it is 1 to 1 or not, whether it is onto or not, whether domain is equal to codomain is a requirement or not. So when we say monomorphism, it is 1 to 1. It is not onto. Domain equal to codomain, it is optional. It is, if it is there, fine. If it is not there, fine. Now, in case of epimorphism, it is not 1 to 1, but it is onto. Endomorphism, these two doesn't matter. What matters is that the domain is equal to codomain. Endomorphism, it is 1 to 1 and it is onto. And domain is equal to codomain. And isomorphism is 1 to 1 and onto, but not necessarily domain equal to codomain. This is a very, very powerful concept of homomorphism. In the next few sessions, we will be looking at it in more detail. So that was homomorphism. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.